would like to thank my students, my sponsors, and our collaborators, without whom this work wouldn't have been possible. So, I won't start with the motherhood and apple pie slide, because we have already heard through the rest of the presentations. Instead, I will just directly dive into the topic, which is how do we improve computing performance. Now, before we improve computing performance, first we have to define what is computing performance, because there is a lot of confusion about what is performance. And for this presentation, I will define performance as the product of energy and execution time. And the reason for that is there are many ways to improve energy at the cost of execution time. For example, you could reduce voltage. There are many ways to improve execution time at the cost of energy. For example, you could just go for parallelism. But there are very few ways to simultaneously improve energy and execution time. So that would be our metric. And now let's see, how do you improve computing performance? Now, if I were in the Allen building of Stanford, I would say, well, you build better devices to improve computing performance. Now, what happens is, while there are many ideas for better devices, there are only very few experimental demonstrations of real systems that are built out of these new devices, number one. And number two, the device is not the same thing as a system, as we will see very soon. Okay. So if I were more on the architecture side, the Gates building, I would say, well, the way to improve computing performance is by playing what I call design tricks. We already played the multi-core trick. Right now, we are playing the accelerator trick. And of course, we have power management, thermal management, and so on and so forth. The trouble is, there are very few tricks that we have in our toolbox. And we are already playing those tricks today. And oh, by the way, when we play those tricks, what ends up happening is the design complexity blows through the roof. And that's why I have seen so many ideas that never saw the light of the day, because simply designers didn't know how to verify those complex design techniques. So now, if you think about how do we improve computing performance, remember performance means energy times execution time. And how do we improve computing performance by 1,000 times? Neither one of these, either better devices or these design tricks, they cannot get you to 1,000x, and that requires new innovations. And the specific innovation that I'm going to talk about today is what I call a nanosystem. What is a nanosystem? Well, first of all, it starts with nanotechnologies. Now, when you think of nanotechnologies, people tend to think about devices. But it's not just devices. It's also about new fabrication techniques. For example, I will talk about something called layer transfer today. Or even new sensors that could augment the capabilities of our systems. Now, nanotechnology is kind of interesting because on one end of the spectrum, you're talking about things that are really, really small. I'm going to talk about carbon nanotubes, for example, at a 1 nanometer scale. And on the other end of the spectrum, you're talking about things that would be like hundreds of billions of those really, really small things. And when you have billions of those really, really small things, you have to worry about imperfections, you have to worry about challenges with large-scale fabrication, you have to worry about variability and so on. And when you are successful in overcoming these challenges, you must make sure that you build a new architecture that is not possible with existing technologies. Because if you just simply replace existing components with these nano components, still the architectural bottlenecks would still remain the same. And that does not give the 1000x level kind of benefits that we are shooting for. And obviously, these new architectures should enable new applications. I don't have to preach to the choir over here about new applications because the previous speakers already talked about it. So these are the so-called abundant data applications going all the way from the edge all the way to the cloud. Now, if you think of these abundant data applications, what are some of the commonalities? The first commonality is what is called the memory wall. And intentionally on this slide, I did not write whether I'm talking about execution time or energy, because it doesn't really matter. Only 5% of the energy or the 5% of the execution time is spent only in the computing itself, 95% is spent trying to access memory. And oh, by the way, while many people have observed this, they go and try to complain about Dr. John von Neumann, right? And this has nothing to do with von Neumann architecture. Because even if you take a hardware accelerator, non-programmable, which is a non-von Neumann architecture, that hardware accelerator would have the exact same problem of the memory model. So it doesn't really matter whether you're talking about von Neumann or non-von Neumann, you have this challenge that you have to overcome. And when you think about other brain-inspired computing models, for example, for machine learning, beyond classical neural nets, you have the same challenges. How do you think about computation in memory? How do you think about dense connectivity, energy efficiency, footprint, and so on? So what we are doing in our project is this so-called next idea. But before we get there, first let's talk about how do we think about computing systems today or chips today. Chips today are really boring because they are just a two-dimensional fabric with a bunch of wire stacks, basically. Instead, in our system, in our chips, what we have in the next chips are these three-dimensional structures where you have layers of computing logic, layers of memory. You could even have a layer of sensors, for example, to augment capabilities. But if there was one thing that I wanted you to take away from this presentation, that would be an ultra-dense and fine-grained three-dimensional integration, which is not your through-silicon vias or your chip stacking. So this is something that is impossible with today's business as usual, the way we think about chips today. So a few years back, in December of 2015, we had a position paper on this next idea, which stands for Nano-Engineered Computing Systems Technology. And in the January issue of this year's Proceedings of the IEEE, we actually have a much detailed description of this next idea that I would encourage you to read. But delving into the next level of details, this is sort of how our vision of this next architecture is. So as I said, you have layers of computing logic, and for logic devices, we focus on one-dimensional carbon nanotube transistors, and also we look at two-dimensional materials, although today's presentation is going to focus on carbon nanotubes. And you can see the layers of logic. For memory, on the various three-dimensional layers, we look at MRAM and resistive RAM because they have complementary properties with respect to endurance, with respect to retention, with respect to density and capacity. But a couple more really important things is the ultra-dense and fine-grained vertical connectivity that is achieved without any through-silicon vias, number one. And number two, this entire structure, as I will show you through this presentation, is completely silicon compatible. That means you can build it in a silicon fab. You do not have to throw away existing infrastructure to build this system. Another important point I would like to emphasize. When people think about logic on the upper layers, the immediate thing they think about is, oh my goodness, how do you get the heat out when the system is running? Now remember, when you have logic on the upper layers, that logic could do many different things. And in the first generation of our next architecture, the logic on the upper layers are mostly used for memory accesses, which means memory access circuits, memory controllers, and the NOC. And you do not have heavy-duty computing running on the upper layers. That's still running on the first layer, which is close to the heatsink. So while thermal is eventually a challenge that you have to worry about for any kind of a three-dimensional system, for the first generation of our next architecture, we do not have to worry about thermal challenges. So this is not just a concept. So as part of DARPA's 3D SoC program, this is jointly between MIT, Stanford, and a real commercial foundry, which is Skywater Technology Foundry, which used to be the old Cypress Foundry. We are actually building these things in a commercial foundry, and things are actually working. So this is not an academic endeavor. So let's get into details. So as I said, when you try to achieve something that's at 1000x level, you have to think of Amdahl's law. Which means that first of all, you have to break the memory wall. But when you break the memory wall, you now have to worry about the computing wall. And you have to improve everything simultaneously so that you get 1000x. So let's start with the computing side of things, and you will see why I start this way, and the memory side will automatically come in. So what are carbon nanotube field effect transistors? Well, carbon nanotubes are one-dimensional nanocylinders of graphene. And typical carbon nanotubes that we grow in our lab have a diameter of around 1 nanometer. And when you grow carbon nanotubes on a substrate, or when you transfer carbon nanotubes from one substrate to another substrate, what you get, once you print the source, gate, and drain contacts, you get a carbon nanotube field effect transistor. Why are we talking about a carbon nanotube transistor? That's because if you take an existing processor, not an NAND gate, a full processor including interconnects and everything after place and route, and if you replace your existing transistors with carbon nanotube transistors and then do a full optimization, you will get a 10x energy delay product benefit right off the bat. And so this is the chart. This is in collaboration with IMEC in Belgium and TSMC. And as you can see, that here is FinFET. So this is energy, this is frequency. You want to have a very low energy and a very high frequency. You see how FinFET goes. A lot of people talk about nanowires and nanosheets as the next transistors. You see that you get some very incremental benefits by doing that, versus carbon nanotubes simultaneously give you a 3x energy benefit and a 3x frequency benefit simultaneously at a full processor level. And not only that, if carbon nanotubes were so good, how come you do not have carbon nanotubes in your cell phones, right? And that's because although the first carbon nanotubes were demonstrated back in 1998, for a very long time, people were not able to actually build large-scale systems out of carbon nanotubes. And that has to do with inherent imperfections of carbon nanotubes. That include misposition nanotubes. So if I was giving this presentation 10 years back, carbon nanotubes would look like a bowl of noodles. And metallic carbon nanotubes that create source-drain shards inside a transistor. So what we realized when we started the carbon nanotube project is that just by doing processing, you cannot overcome these challenges, and that goes back to the point I was making about something very small, but at the same time, billions or hundreds of billions or trillions of those things. Instead, at Stanford, we came up with this imperfection immune paradigm, which is a combination of processing and design that overcomes these challenges with large-scale fabrication of carbon nanotube circuits. And that enabled, so in 2013, we actually built the first carbon nanotube microprocessor. This was a tiny little microprocessor, but actually it was running an operating system, and it was running programs, and it was emulating the MIPS instruction set and so on. This was in 2013, and this last month, my former student at MIT, they actually demonstrated a full RISC-V microprocessor at a full wafer scale, again with carbon nanotube transistors. So I often joke that while carbon nanotube processors grow up, human beings also grow up, because this is Max Schulacker, who was a student at that time at Stanford, and this is the same Professor Schulacker at MIT. He grew up, the carbon nanotube processors grew up too. But that's carbon nanotubes, and that's going to get you a 10x TDP. And when we started this presentation, I promised 1000x. So what is the path to 1000x? And that's where three-dimensional integration comes into play. So how does three-dimensional integration happen today? That's by mostly chip stacking, using through-silicon vias. Now, the way I think of through-silicon vias is the way I think about if I have to drive between San Francisco to Berkeley. Both are quite populated cities, but there are only 3 bridges, right? The Dumbarton Bridge, the Bay Bridge, and the San Mateo Bridge, and maybe the San Rafael Bridge, right? 4 bridges maybe. And that's why it doesn't really matter what time of the day you drive, you're always stuck in traffic, right? So similarly, this is exactly what's happening with today's chips. Because you have, thanks to Moore's law, you have, massive number of transistors on your computing substrate. You have massive number of transistors on your memory substrate. But even if you think about the through-silicon vias, Those are like the 3 or 4 bridges between San Francisco and Berkeley. And that's why the traffic is always stuck. And that's why you do not get enough performance benefits. Instead, what you want is millions of bridges between San Francisco and Berkeley so that you are never stuck. Similarly, millions of vertical interconnects, the densest possible vertical interconnects between computing and memory. What are the densest possible vertical interconnects known to mankind? Those are actually the existing back-end of line interconnects that are already there, the vias, the interlayer vias that are already there inside our chips. So why don't we make use of them? Now, if we have to make use of them, we have to use something called a monolithic three-dimensional integration. And which means that we have to put transistors and memory cells on the upper layers of our chips. Although today we just have interconnects on those upper layers. And why don't we put transistors and memory cells on the upper layers of our chip? Well, we do not, because to build a transistor, a silicon transistor on the upper layer, it takes around 1,000 degrees C. And if you use that 1,000 degrees C to build a silicon transistor, everything underneath that you just built will be damaged or destroyed. So this is where the new transistors like the carbon nanotube transistors and the new memory technologies that I talked about come into play. Because you can build those things at a very low temperature, which means that suddenly you can combine device level benefits together with architecture benefits, and emerging logic and an emerging memory provides a monolithic 3D which enables a new architecture that is impossible with today's existing technologies. Now, is this something that you can actually build? And we showed the first such three-dimensional nanosystem in our lab. This was in Nature in 2017, where this is what we built. We had a carbon nanotube computing logic, that was doing classifications. It's an accelerator. We had a megabit of resistive RAM. We had millions of sensors. So this chip actually had more than 2 million carbon nanotube transistors to show that things are actually scalable and actually you can build very large-scale systems over carbon nanotubes. And as I said, the most important point of this presentation is the ultra-dense and fine-grained three-dimensional integration, no TSVs. And as a result, what this chip was doing is why is this thing not moving? Okay, so it can actually collect terabytes of data per second from the external world, those sensors, they were sensing gases, and that data was being stored in the on-chip resistive RAM, and the classification accelerator, which was on-chip, was performing computation on the on-chip memory and producing results that were extensive and accurate. And this is often the dream that people talk about at the edge: collect a lot of data, store it in situ, and perform computation right there without having to move data back and forth and pay an energy price. Okay, and that is not the only example. Here is another example of what is called a hyperdimensional computing, which is a computing model for brain-inspired computation. And similarly, the whole point is to show that there are many such possible nanosystems using carbon nanotubes and resistive RAM and the monolithic three-dimensional integration that I was talking about that you can build in real situations. And this is not just a fantasy story that you cannot actually build. So I could end this talk right here, and I could say, well, my way or free way, right? You use carbon nanotube transistors, you use magnetic RAM on the next architecture with hard RAM, and that's it. But actually, I know that many of you in this audience might have other ideas for other RAM technologies, maybe even logic technologies, maybe even integration technologies, which means that while we push the hardware side of things, where we actually build actual prototypes, we also have an extensive simulation framework, which is the next simulation framework, where on one end, we bring in heterogeneous nanotechnologies, a wide range of nanotechnologies, maybe the ones that we do not even build in our lab. On the other end, we actually bring actual workflows, for example, TensorFlow and others, and then we actually perform architectural exploration. We actually look at system level design, and at the same time we actually have a place and route flow in our lab although there is no existing EDA tool that can actually, actually provides, pleasant route using monolithic 3D, but we created our flow basically reusing existing EDA tools. And as a result, we can actually tell you what the yield would be, what the variability would be, what the energy would be, what the capacitance situation would be, how is the execution time going to look like, how is the temperature, so on and so forth. And if you look at the numbers, you will see that for a wide range of applications, not just deep learning, graph analytics, you look at processors, you look at accelerators, for a wide range of applications, you see simultaneously significant improvements in energy and execution time at the range of the 1000x that I was talking about. And here is my second important point that I want you to remember. The first was this very ultra-dense and fine-grained 3D. And the second important point is, you can get all these benefits without having to change the existing software. Because we all know that if we have to change the existing software, that's a lot of pain in the neck. Which means that there are many nanosystems opportunities that this creates. Cross-layer optimization between device level, circuit level, architecture level. I will not have the chance to talk about dense compute and thermal solutions when you actually run heavy-duty compute on the upper layers. And I will not have the time to talk about new software optimizations. Maybe for a future presentation, we can talk about that. But before I wrap up, I will say a few words about this cross-layer device and circuit and architecture level optimization using the example of resistive RAM. So we were very fortunate that in collaboration with CEA in Grenoble, France, on top of ST Silicon, CEA actually put their RRAM, and as a result, at ISSCC earlier this year, we were actually able to demonstrate for the first time a full system with resistive RAM that could store multiple bits in each cell of resistive RAM. And actually we could make use of that multi-bit storage to actually improve the accuracy of neural nets on the same hardware. And of course that requires a lot of interaction between circuits, because typically the way people would think about multiple bits per cell for flash would not work for resistive RAM. You have to think about architecture and even application, how you encode your weights, so that in case there is an overlapping distributions of multiple bits per cell, still you're resilient and you are actually improving the overall inference accuracy. And at IETM, later this year in December, we will have even more exciting result, which I guess we are not supposed to talk about in this presentation. And a last example of such cross-layer optimization is people often worry about, this RRAM, it has low endurance, will it work for 10 years? Again, using an algorithmic technique and an architecture technique, we could actually overcome the endurance challenges, and as a result, we could show at the ISSCC paper on real tests that we can actually run it for an equivalent of 10 years. Yeah, you can ask me during Q&A that how could we run it for 10 years when we had the chip for a few months. Okay, so the last point I would like to make is these are again not some fantasy technologies. At the ERI Summit back in July this year, this is Professor Matt Schulacher, he's the PI of our project. He actually brought in the first industry foundry wafer that's a monolithic 3D integrated carbon nanotubes, resistive RAM, on a monolithic 3D. So to end this presentation, here are the key takeaways. First of all, nanosystems can be built today, and people talk about this lab to fab. That has already happened. These technologies are actually working in an actual commercial foundry. And actually, there is not only one foundry, there is actually another very important company that I'm not allowed to name, where some of these technologies are also working in their fab. The second point is, Sam Fuller, he did a study for the National Academy of Sciences, asking, what's the future of computing performance? Is it game over, or we go to the next level? That was the title of that book, and I would encourage you to read that. And my answer to that is it's game on to the next level, where next is this N3XT technology that we are talking about. And the key point is, it's not just a technology for the sake of a technology. You get massive benefits for a wide range of applications, not just neural nets, using existing software, which means you do not have to change your software. Thank you very much for your attention.